Good afternoon to everyone. The next series of the topic stereochemistry and reaction mechanism. Today I am going to discuss a very important topic in this chapter is projection formula and conformational analysis. So after seeing this video, the student can understand what is the definition of this projection formula and what are types of the projection formula and how we can convert one projection formula to another projection formula. So I will discuss those things with some examples. So after that, the students can understand what is meant by conformation analysis and what is the application of this conformation analysis in stereochemistry with some example. So what is meant projection formula? So in stereochemistry, mainly the stereochemistry is the study of chemical compound in 3D perspective. So with help of this projection formula, so I can visualize the 2D structures into 3D structures. So in this chapter mainly we will discuss how we can draw this 3D compound into 2D form and as well as 2D form into a 3D form. So in this projection formula we have very important projection formulas such as flying wedge projection, Newman projection and Sauer's projection and Fischer projection. The first one is flying wedge projection. So this flying wedge projection is a projection of 2D structures into 3D structures. So I can draw the 2D compound into a 3D perspective. It was explained by this flying wedge projection. So if you see this compound, the two bond, it is in is a normal bond. For example, CH3 it is in a normal bond. It indicates that the two bonds it is in the plane of paper. One paper, the CH bond, it is drawn as a thick bond. So it means that CH bond is very close to me, very close to the observer, and the dotted bond, that means the wave bond is away from the observer. So this is a correct projection of flying wedge projection. So you can draw the methane molecule in this projection by taking two CH bond, by putting a normal bond. It means that it is in the plane of paper, and one bond you have to put in the thick bond. There is nothing but solid bond. So solid bond indicates that CH bond is very close to the observer, or it's coming towards the observer. The dotted bond means is away from the observer. Is the correct way of writing the 2D compound into a flying wedge projection. So next projection is Newman projection. So Newman is a scientist. He visualized the 3D compound into a 2D perspective. So what he is saying now, for example, if you take the ethane molecule, it contains two carbon, and the carbon which is very near to me, that carbon you have to keep in you have to keep your eye in such a way that that one of the carbon is very close to me. You have to indicate that close carbon as a small dot. Okay, the away carbon, you have to denote that carbon as a circle. So if you see here, the dotted is nothing but that is a front carbon, and the circle is nothing but the carbon is away from the observer, that is out of sight. So this is the right way of the Newman projection. So in this formula, the molecule is viewed from the front. The carbon atom away from the observer is called a rear carbon, and it is represented by a circle. And the atom, the carbon atom which is facing in front of the observers, you have to represent by a dot. So dot means that carbon is very close to the observer, and a circle means it is away from the observer. The remaining bonds should be a small straight line. This is nothing but the Newman projection. So for example, you take butane molecule. It contains 4 carbon, CH3, CH2, CH2, CH3, and you have to keep your eye very close to the one of the CH2 carbon. So the CH2 which is very close to me, you have to indicate that carbon is a small dot, and the carbon which is away from me, you have to indicate that as putting a small circle. And for this butane molecule, we have two different conformations, and conformations nothing but we will get different stereoisomers by the free rotation of the carbon-carbon single bond. So for butane molecule, if you rotate the CH2 carbon, you will get two different conformers. One is staggered conformers and another one is eclipse conformers. In this staggered conformers, both the CH3s are away, are very far away from each other. In eclipsed conformers, the two CH is very close to the both the methyl groups are very close to each other. So these are example which is visualized in the PPT. Okay, and next one is a SAW aspersion. So what is my SAW aspersion? The SAW aspersion, Newman position is very close. There's some minor differences there. What SAW is saying now, for any carbon, for any compounds, if it contain two carbon, means one of the two carbons you have to indicate like a Y shape. You have to indicate like a Y shape, and the carbon which is very close to me and you have to away from me, you have to indicate both the thing is like a Y form, and you have to place other atoms in it surrounds the Y group. So the bond between two carbons is shown by a stronger diagonal line because we are looking at this bond from an oblique angle. So the bond linking other substance to this carbon are showing projection above and below this line. So this is the SAW aspersion. So Fischer position is a very effective way to see the molecule more than one chiral carbon. So in a Fischer position and the atoms which is very close to me, I have to put in a horizontal bond, and the atom which is away from me, I have to put in a vertical bond. So for example, in Fischer formula, two like groups on the same side means a erythro, and the two groups opposite side is a 3O group. So the vertical bonds represent bond extending in a plane of the page, where the horizontal line represents bond extending out of the plane. You see, if you see here, if you put it's contain two bonds. One is a vertical bonds and another horizontal bond, and the group which is placed in a horizontal bonds are very close to the observer, and the atom which is placed or which is kept in a vertical bonds are away from the observer. It is visualized by putting in the thick bond and the dotted bond. So you can rotate the Fischer position by an angle of 180 degree on the plane, because so out of plane rotation is forbidden in the Fischer position. It is visualized in this compound. If you take this ClCH3 BrCH3 that is equivalent to the thick bond dotted bond. The group which is present in the vertical bond is you have to put in a dotted bond. Horizontal bond you have to put in a thick bond, and you have to rotate, and you will get the same another side of molecule. Both are same. However, the similar rotation by an angle of produce non-identical structure. So 180 degree rotation means you will give the same rotation of Fischer position by an angle of 180 degree about the axis which is perpendicular plane of it gives identical structures. However, the similar rotation by an angle of 90 degree produces non-identical structures. So this is a capital D and capital L projection formula, because small d and small is different and capital D and capital is different, because capital D and capital L is a relative configuration which is came by taking the glyceraldehyde as a reference compound. So in case if you take the glyceraldehyde, it contains one chiral carbon, so I will get two stereoisomers, because 2 power n isomers I will get. N is 1 means you will get two isomers. Both isomers are seen here. In D-glyceraldehyde, the OH is on right hand side, and L-glyceraldehyde, the OH is on left hand side. So I can apply this for carbohydrates and amino acids. And if you see the structure of D-glucose, it is very close to the D-glyceraldehyde, because this capital D and capital S confidence is applicable only for the penultimate carbon from bottom side, not from the upper side, not from the aldehyde side. From bottom side only you need to apply. So if you take CH2O, next carbon, the OH is on right hand side means you have to assign capital D configuration. So in case for penultimate carbon from bottom side, if OH is on left hand side means you have to assign capital L configuration. Same you can apply for amino acids also by taking the reference of NH2 group. If NH2 group is on right hand side means that is capital D amino acid. If NH2 is left hand side means capital L amino acids. So all naturally occurring carbohydrates are capital D configuration, and all naturally occurring amino acids are capital L configuration. So this is the entire outlook of all the Persian formula, and you can convert one Persian formula into another Persian formula. So for example, if the given component is given in a flying wedge Persian, means you will convert that into a 2D form, and then you have to convert that into a Fischer Persian. So the bond which is in the vertical and horizontal. Horizontal means you have to put in a thick bond, and the component which is present in vertical means you have to put in a dotted bond. So for example, if you see here the CH3 and OH, it is in the horizontal band, and the remaining one is a vertical bond. This is a Fischer Persian. So you can convert that a flying wedge into an this Fischer Persian also, because CH3 is very close to me and hydrogen is away from me, and you have to rotate that one, and you have to keep in such a way that both the CH and hydrogen are very close to me, and COH and OH is away from me, and you have to convert that into a Fischer Persian. And you have to convert the Fischer Persian into a Sahas-Newman Persian also. Actually, it's very easy, because the eclipsed form of Sahas and Newman Persian is very close, is equal to the Fischer Persian. It is visualized here, and because here one carbon contains OH and hydrogen, and the backward contain hydrogen. It is in a it is in anti form. You have to rotate, and you have to get the eclipsed form, because eclipsed form is equal to the Fischer Persian, and the converting of Sahas and Newman Persian is very easy. It is visualized in this PPT. And the next topics I am going to discuss conformational analysis. So what is my conformational analysis? Conformational analysis is a 3D arrangement of atom, and I will get the 3D arrangement of atom by the free rotation of carbon single bond. So conformer is a specific conform, rotation is a single bond, and if you see the classification of the conformer, we have get different stereoisomer by rotation of a single bond, and we have a amine inversions also. So the molecules is constantly rotating through all the possible conformation. Because of this rotation, I will get different conformers. Some of the example has given here, and here if you take the ethane molecule, in ethane molecule we have two different conformers. One is the staggered conformers, another is the eclipse conformers. So if you rotate the ethane molecule, you have to keep one carbon as a constant, and you have to rotate the backside carbon, or either ways you can do. So the point is, you have to keep one CH3 bond constant, and you have to rotate. So if you rotate, I will get different conformers. One of the conformers is a staggered conformers, another conformer is a eclipse conformers. Eclipse conformers, each CH bond, the front CH bond is eclipsing the backside CH bond. So the observer cannot see in the backside CH bond. That's why it's called as what? Eclipse conformers. And the staggered conformers is both the hydrogens are in the 80 degree, and is very stable conformers, and you have to see in that one in a Sahas Persian. So staggered conformers is very stable one, because the CH bond is far away from each other. So this is the staggered conformation. What is my staggered conformation? The conformation about the carbon single bond, in which atoms or groups are as far apart as possible from the atoms. So example are seen here, ethane molecule, and we have the eclipse conformers. Eclipse conformers, CH bond is eclipsing each other, and this is the visualization of this ethane molecule, and you have to write that ethane in a dash wedge formula also. So dash wedge formula means one CH bond is very close to me, that CH bond you have to indicate in a thick bond, and the CH bond is away from me, you have to indicate that CH bond is a weak bond, and the remaining CH bond which is present in the plane, you have to indicate in a normal bond, which is visualized in this PPT. And you can convert that Sahas as a dash wedge in a Sahas as well as Newman Persian also. So if you see the two different conformers, eclipse conformers is highly unstable because the torsional strain is higher in this eclipse conformers. So what is my torsional strain? Torsional strain is otherwise called as what? Eclipse instructional strain, and the strain that arises when non-bonded atoms separated by 3 bonds are forced from their staggered conformation to a eclipse conformation. So torsional strain between eclipse and staggered ethane is approximately 12.6 kilojoule per mole. So this is the conformation analysis. If you see the eclipse and staggered, the angle between the CH bond is 60 degree. So diaedral angle is 60 degree. Because the diaedral angle is 60 and less torsional strain, this staggered conformers is more stable. And this is the energy profile diagram of different conformers of ethane molecule. The number one is eclipse is higher in energy and it will rotate to give the staggered conformation, which is lower in energy. Then once again it is moved to the eclipse and staggered, it will go as such until it came to the staggered conformers. So this is the energy profile diagram, and the y-axis energy and x-axis is nothing but angle of rotation. At 0 degree of rotation, the compound ethane is present in eclipse form, and if rotated after 60 degree, it will convert into an anti, and 120 degree it will go to the eclipse, it will go as such. And this is a conformation analysis of butane molecule. And if you number the butane molecule, first carbon, second and third 4, and I am going to visualize the second carbon and third carbon and the carbon 2 and carbon 3. And the carbon 2 and carbon 3, it is in the plane of board, and the CH3 and CH2 in one structure they are very close to it, they are eclipsing. And another structure, after rotating 60 degree, it will give both the CH3 at an angle of 60 degree. That's called as Gauss conformation. And if you rotate once again, I will get the partially eclipsed conformers. And if you rotate once again 60 degree, you will get the anti-conformers. And once again rotate, I will get the partially eclipsed, Gauss, and the fully eclipsed. So this is the different conformers of the butane molecule, and you can plot the energy profile diagram for this compound. So we have eclipsed butane, and eclipsing is the conformers higher energy because both the methyl groups are eclipsing each other. The calculated energy difference between the both A and B is approximately 0.6 kilojoule. So this is a conformation analysis about single bond, which is clearly visible here, and we have A, B, C, D, E, F, A, all are different conformers. We have fully eclipsed, we have a Gauss, partially eclipsed, anti, and it will go as such. It is visibly seen here. And if you see the angle strain, the strain introduced in the molecule and the bond angles, ideal tectonic bond is 109 degree, and we have two different strains, torsional strain and steric strain. The strain caused by the repulsion between the bonding electrons of one substituent and the bonding electrons of a nearby substituent is called as torsional strain. And if you see the steric strain, means the steric strain caused by atoms or group of atoms approaching each other too closely. So and we can plot the energy profile diagram of different conformers of butane. And here the eclipsed at the angle of 0 degree, you can see the eclipsed, and after rotation of 60 degree it will move to the Gauss, and after 120 degree is moved to the partially eclipsed, and anti 240 degrees partially eclipsed, once again Gauss and eclipsed. This is the energy profile diagram of butane molecule. And so if you see this cyclobutanone structures, you can draw the two different structures, which is clearly visible. So this is the important about the conformation analysis. So the remaining things we will see in the next.